All right, today we're going to tackle one of the absolute deepest mysteries in all of physics, the problem of vacuum energy. It's a puzzle so huge that it puts our two best theories of the universe in a direct and I mean spectacular conflict. So let's just dive right in.
So let me just kick this off with a really big question. What is the single biggest error in the entire history of science? And look, we're not talking about some small miscalculation here. We're talking about a disagreement so ridiculously vast, it actually challenges the very foundations of how we think reality works. And the source of this epic error? It's a fundamental clash between our two great pillars of physics, general relativity, which is our theory of the really, really big stuff, and quantum mechanics, our theory of the really, really small stuff. The problem is, when they both try to calculate the energy of totally empty space, they give answers that are, well, they're not even in the same ballpark. They're not even in the same universe. And you can really see the scale of the problem here. If the theoretical value were the height of a skyscraper, the observed value would be smaller than a single atom. It's a discrepancy of over 100 orders of magnitude. This isn't just a simple mistake. It's a giant flashing sign telling us we're missing something absolutely fundamental about how the universe works.
So let's really break down where this massive, massive error comes from. It all boils down to two completely different ways of trying to calculate the exact same thing, the energy of nothing.
On one side, you have a theoretical value, something predicted by everything we know about quantum physics. And on the other, you have an observed value, something we actually measure by looking at the expansion of the entire cosmos. And these two numbers could not possibly be further apart.
I mean, how do you even measure nothing, right? Well, let's get into the two methods physicists use and the absolutely jaw-droppingly different answers that they spit out.
So you've got these two competing approaches. The observational method is kind of top-down. You look at the whole universe and work your way backwards. The theoretical method is bottom-up. It tries to add up all the teeny-tiny little energies predicted by quantum physics. The problem is, they don't even come close to meeting in the middle.
Okay, first, let's talk about the observed value. By measuring how fast our universe is expanding, cosmologists can actually figure out the energy density of empty space. You know, what we call dark energy. And the number they get is incredibly small, about 6/10 billionths of a joule for every cubic meter. It's this tiny, tiny amount of energy that's gently pushing the universe apart.
And then you have the theoretical value. According to quantum theory, empty space isn't empty at all. It's this buzzing, fizzing sea of virtual particles that are constantly popping in and out of existence. Now, when you try to add up all the energy from all these fluctuations, you get an absolutely colossal number, a 1 followed by 96 zeros. It's just insane.
To put it mildly, as one of our sources says, this is a big difference and unexplained yet. Yeah, a big difference has to be the understatement of the century. This isn't a rounding error. It's a sign that our understanding of the universe is deeply, deeply flawed. And look, this isn't just some quirky academic puzzle. The sheer, mind-boggling scale of this error points to a genuine crisis in physics, one that really challenges the very foundations of everything we've built. And yeah, this whole mess has a name. It's called the cosmological constant problem. It's often called the single worst theoretical prediction in the history of physics. And honestly, it's a major roadblock on our path to a unified theory of everything. This problem is what's known as the most severe hierarchy problem in physics. Basically, our theories have absolutely no way to explain why these two values are on such wildly different scales. It's a clear signal that our understanding of space, of energy, and of the vacuum itself is just fundamentally incomplete. So, how do we get out of this mess? I mean, where do we even begin? Well, some physicists are proposing a really radical shift in how we look at things. What if we've just been thinking about the universe all wrong from the very beginning?
There's this new conceptual model that says we should stop thinking of the universe as a container with things in it. Instead, we should start thinking of the universe itself as a single, indivisible object, an elastic fabric of reality.
Okay, so this new model has three core ideas. First, the universe is just one singular object. Second, all the stuff we see, matter, light, you, me, we're all just local reshapings or different states of this one fabric. And third, and this is the real key, vacuum energy isn't the energy of empty space, but it's simply the total energy of the fabric that's left over after you account for all the matter and light.
And this conceptual shift, it completely reframes the whole problem.
It doesn't even try to fix the old, broken calculation. It proposes an entirely new, and frankly, better way to even ask the question.
You see, the old approach, the one that gave us that impossibly huge number, defines vacuum energy as the sum of all the tiny background energies from every single quantum field. The problem is, when you try to add all that up, the sum is basically infinite. But in this new model, vacuum energy is just what's left over. You start with a total, finite amount of energy for the entire universe object, and then you just subtract the energy that's been shaped into the particles and forces we can actually see and measure. And that right there, that is the big conceptual leap. The problem is no longer about trying to add up an infinite number of things. Instead, it becomes a partitioning problem. How does a single, finite amount of energy divide itself between the states we call matter and the background state we call vacuum? It completely sidesteps the whole problem of infinity.
Now, this is a totally fascinating idea, right? But, and this is a big but, it's so important to remember that this is a conceptual framework, not a finished theory. It solves one problem, but in doing so, it raises a whole new set of really tough questions.
And this really gets to the heart of the challenge. For this model to be more than just a cool philosophical idea, we need a way to actually calculate this total energy without falling back on the old quantum methods that got us into this mess in the first place. That part is not at all clear yet.
So, the next steps are pretty clear, but they are incredibly difficult. Physicists would literally need to develop a whole new type of mathematics to describe this fabric. They'd need a way to figure out the energy states from the fabric's own properties, not from quantum fields living on top of it. I mean, this is the really hard work that could turn this incredible idea into a testable physical model.
And then that leaves us with one last pretty provocative thought to chew on. If this model is actually onto something, if the universe truly is a single elastic object, then what is it made of? If reality is a fabric, what are its threats? It's a question that pushes us right to the very edge of what we know. And you know what? That is exactly where science gets exciting. Thanks for joining me.